So this is pretty speculative. It's kind of very it's very future facing. We have to already have a reliably distributed and robust in terms of being able to stay there entanglement network between nodes. But what these authors discuss is saying, okay, once we get past some of these early hurdles, how can we actually think about entanglement and quantum networking as a whole, sort of at a greater level of abstraction, where we can truly begin to take advantage of the weird way that quantum works. And so what this paper basically discusses is different ways in which we can think about not just using networking for quantum, but rather using quantum for the process of networking itself. And so let me discuss what that means. So, okay, just before I get into that, if you have any sort of experience with quantum mechanics or physics, you can think of this as being like a second quantization of the network itself. And to get there, let's first just consider a few facts about entanglement. So, and these are all kind of like things that we already know, but when taken together, they can kind of form a picture that I think is useful. That the authors kind of do as well. So the first thing I think about is that as I said, we usually think about entanglement as being something that say Alice and Bob request that they want to be able to teleport some states. So we say, okay, we're going to generate entanglement, and here you go, and then they use it up to teleport a state, and then it's done, right? And early on that makes sense because entanglement is a difficult resource to distribute. But as we improve and as we're able to have more and more robust entanglement, we can think of that entanglement itself as a form of connectivity, right? Because as you know, right, if Alice and Bob are entangled, then they can teleport a qubit from one side to the other, and so therefore the entanglement itself is a form of quantum connectivity. The whole act of getting entanglement there in the first place is in order to get that connectivity in place. And when you think about the fact that it is a form of connectivity, and the fact that we can actually change where this connectivity is located using entanglement swapping, as we've been discussing, right? You can think of entanglement as kind of like adding to the topological neighborhood of your network, in the sense that if two nodes are entangled, it doesn't matter how they got there. They now have a connection, and therefore, independent of whatever your actual physical quantum network looks like, you now have an additional kind of connection in that network. And so imagining entanglement as like a dynamically shifting topological augmentation of your network is kind of what this paper is all about. Yeah. The other and so the other sort of last key piece of this is that right now, when we think about getting entanglement from A to B, from Alice to Bob, we think of it in terms of the same types of ways that we think of classical networking, right? We have a source and a destination, and we need to find the fastest, the easiest way to sort of the shortest path between Alice and Bob in order to get entanglement there. And that is basically the same form as like finding the fastest path from Alice to Bob in a classical network. And so what the authors point out is that unlike a classical network and a classical message on that network, a classical message is only useful for where it's going, right? Any node who has it and passes it on doesn't care where it is. They're just passing it on. It's only useful to where it's going, to the destination node. Entanglement, once it's established, is not like this, right? It is universally useful, right? If one of the nodes on the path to Bob suddenly needs entanglement a lot more, you can dynamically shift what you're doing and use the entanglement that you were shifting along to then be useful to that third node along the way. Yes. So all of this is to say that we can imagine quantum networking in the future as, there being a physical quantum network, and as part of that, there is a dedicated part which is kind of meant to just be establishing entanglement, and storing it preemptively, right? Once we're able to sort of do that reliably, we can have a physical network with kind of an entanglement overlay of that network. And the way they picture this in going as a first sort of toy model is we'll have the physical network, and then we'll have dedicated supernodes, which will be dedicated to forming lots of entanglement between sort of other supernodes. And the key piece in thinking about this, I mean, so far this all sounds fine. Like, okay, let's get entanglement so that it can be used and have it done in a preemptive way so that it's useful for whoever wants it, and that's great. But once you actually have these entanglement networks and you begin to think of these nodes, not of these supernodes, not as necessarily physical locations that we need to find, but as a piece of an entangled state, i.e., when you think of a network node address as a quantum system as opposed to a classical ID, which is what the title of the paper is all about, then you can actually begin to do much more interesting things. You can not just use the network for getting quantum things happening, but you can use quantum to actually improve the functioning of the network itself. And so one of the strangest ways that and there's many different ways of sort of imagining what we could do with this. But in general, what happens is that whereas when you send a piece of quantum information, a qubit, it can be a 0 and a 1 or a superposition of in between. Now we're thinking about quantizing aspects of the network, and so the network itself becomes, like, for example, which path a quantum message actually takes along that network could itself become a quantum thing, where the photon that is carrying a piece of quantum information can be actually not along one path or the other, but distributed in a superposition along both paths. And this is a real thing. In general, like superpositions of paths or temporal orders or superpositions of the orders of operations that you can do is a real thing. And when this happens, you open up a Pandora's box of different things that you can do, which we are just at the beginning of exploring. In terms of actually getting, in terms of quantum paths and getting, a qubit from A to B, doing it in this sort of more global sense has huge implications for noise suppression and basically quality of networking, right? Because you're able to sort of utilize the whole quantumness, and in that way, it's less sensitive to noise at individual parts of the network in a sense, right? Anyway, I know that's weird, but it is something that can happen, and so you can imagine that once we sort of have these large overlay networks of entanglement, it can be pretty exciting what we can do.